record this because the next period class I have to go leave school for an hour, so I have to record and make sure my fourth period watches this. So this is going to be posted after this. Okay? So this is all about logarithmic functions. Many of you guys already have seen logarithmic functions, hopefully. Okay? Y equals a to the x is called an exponential function. Okay? Because this function, if I were to graph it, it's 1 to 1, meaning for every x there's exactly one y. It must have an inverse. Okay? And the inverse looks like this. Remember, an inverse is a reflection over the line y equals x. Okay? This function here is the logarithmic function. It's the inverse of y equals a to the x. Do you guys remember how I find an inverse? How do I find an inverse? You switch the x and the y. So this is the same as x equals y a to the y. Sorry. Okay? X equals a to the y. But it turns out it's very difficult to figure out what y is. So people figured out a program or an algorithm to figure that out. And that algorithm is called the logarithm. Okay? And so another way to write this same thing, x equals a to the y, is y equals log base a of x. Okay? So this is equivalent to saying this. So when they say rewrite the logarithm in exponential form, this is called exponential form. Okay? And this is called logarithmic form. Okay? And it's the same. What? Okay? And these two things mean the same thing. The nice thing about this is I could plug in an x value and get out a y value. And your calculator will do that for you. Okay? So you can plug in a value for x, saying what is the exponent that I can raise a to in order to get some number. Okay? This says if I take the log of some number, what is the exponent? So a logarithm is, when you're solving a logarithm problem, you're finding an exponent. And that's why very, very large numbers are expressed as, or very, very small numbers are expressed a lot of times as logarithms, like earthquake Richter scales, and what else, like decibels of sound and stuff like that. That's why they use logarithms, because you could express very large numbers in kind of shorthand. Okay. When we write this thing here is called. This is called the a. Let me rewrite it over here. Y equals log a of x. This thing here is called the base. Okay. If there is nothing there, if they just write y equals log of x, it's under, this is called the common logarithm. Okay? Common logarithm, and this is base, the base is 10. Okay? And that's the one that's on your calculator. There's two logarithms that are buttons on your calculator. One is base 10 log, and one is base E log, okay, which is the natural log, okay, which some of you already know, okay. So, how does that work? So if you have something like this, so you will have logarithm problems without a calculator. So if they say find the log of 100. Anyone tell me what that is? That's right, Christian. 2. Do you guys understand where Christian got that? Okay. So it's understood there's a base 10 down there, right? So there's a base 10. So this says, if I rewrite it, so you got to kind of think about it like y is over here. So what I say, 10 to what power equals 100? Okay, 10 to what power equals 100? 10 to the 2 power. Okay, so this is 2. Okay? If you were to take log of 100, right here, log of 100, and plug it into your calculator, you get 2. Isn't that cool? Okay, so so that's what that means. Okay, how about this one? We'll try some more trickier ones. Log base. Oh, I shouldn't write red. That's bad. Bulls will attack me. Log base 2 of 0.25 equals question mark. Anyone know what that is? So what I do when I do this, I rewrite these problems in exponential form. I say 2 to the y power equals 0.25. So, anyone? Yes?
Would it be 1/2?
It wouldn't be 1/2 because that would be the square root of 2. Close. No one? Deanna?
-2.
-2. 2 to the -2 power equals 0.25 because 2 to the -2 means 1 over 2 to the 2, which is 1/4, right? Which is equal to 0.25. So that's kind of a tricky one, okay? But you'll get used to doing the. What you might do is say, okay, well, 2 to the y equals 1/4. What's y, right? So it's got to be a power of 2. And I could think of it this way. I could say, well, that's 2 to the y. This is 2 to the -2. So y has to be equal to -2. Right? Another way to think about it. Okay. Here's a similar one. What would be log base 3 of 1 over 81? You can do it. Bigger.
-4.
-4, right? So again, you say 3 to what power equals 1 over 81. Well, I know that 81 is a power of 3. I could rewrite this as 3 to the question mark equals 3 to the -4 because 3 to the +4 is 81. So 3 to the -4 would be 1 over 81. So question mark equals -4. Okay, I like those ones where you don't have to use your calculator. And we'll learn in a minute, like some of the newer calculators, they could do other bases than 3 and 10. But I don't want to really teach you that because I want you to use the change of base formula that we're going to learn about. We're going to learn about tomorrow. Okay, so that's it. Here's some properties of logarithms that you should know. Properties of logarithms. Properties of logs. Log base A of 1 equals something. Who knows what that is? A to what power equals 1? 0. Okay? So if you try to take the log of 1, you can, on your calculator, you get out 0. Okay? 2 is log base A of A equals, A to what power equals A? 1. Okay? 3, log base, so this is log base A of A to the X is equal to A. Okay? A to what power equals A to, so A to what power equals A to the X? A to the X power equals a to the x. So, wait. Whoops, that's wrong. X, right? So I answered my own stupid question, okay? That's x. So if you see something like this, log base 6 of 6 to the 20th, what's that equal to? 20. So the base, taking the log of something raised of the same base raised to some exponent, just takes that away. Conversely, this is kind of a more confusing one to prove, but exponentially, a to the log base a of x is equal to, guess what? X as well, okay? Because these are inverses of each other, right? The logarithm undoes the exponential function. So whatever I take here, plug it into here, you get out the same thing. Likewise, if I take this and raise it to the log base a of x power, I get out x. So the logarithm and the exponential to a log take away the exponential and the logarithmic thing. Okay? Graphs. Ready to learn about graphs? Sure. Graphs of logs. Graphs of f of x equals log base a of x. So I already kind of indicated it, but because it is a inverse of the exponential function, so if I were to graph, I'm going to graph the line y equals x. Oh, let's undo that. Let's make it dotted. That's not dotted. Oh, I need to go down. So, if this is y equals x, okay, and this is y equals a to the x, a to the x, then the logarithm function down here kind of goes like this, okay? It's a direct flip of this over the line y equals x. So since this has the point 0 comma what on it, 0 comma 1, y equals log base a of x, this has the point what? 1 comma 0, okay? Because this has an asymptote at y equals 0, this has an asymptote at x equals 0, okay? So with a log function, it has a vertical asymptote. So I'll write down all these things in a second, okay? If this has the point 1 comma 10 on it, then this would have the point what on it? 10 comma 1 on it, okay? If this has the point negative 1, 1 over 10, then this has the point what? 1 over 10, negative 1, right? Is that right? 1 over 10, yeah. 1 over, that's not a very good scale, but 1 over 10, negative 1, okay? So here's some properties of logs. Domain. The domain goes from 0, not including 0, up through infinity, okay? The range goes from negative infinity to infinity. Right? You can it goes up slow, but it goes up forever. Right? With logarithmic functions, they go up kind of slowly, but they go up forever. Okay? X-intercept 1, 0, and vertical asymptote, asymptote at x equals 0, and it's always increasing, okay? Meaning it's always got a positive slope, Right? It's always going uphill, even though it goes uphill slower and slower and slower as you get further and further away. It's always going up. So you can plug in huge numbers, right? That's why they're powerful for like earthquakes and stuff, right? You can plug in 10,000 to base 10 log, and you'd only get out, what's 10,000? 4, right? It's only 4 on the scale, so it would be the point 10,000 comma 4 on your graph. So logarithms go up, y values go up very slowly. All right? Oh, we're not done yet? Oh my goodness. I'm sorry. So then we're going to talk about sketching the graph. Sketch. That's so sketch. Log base 2, base 10, not base 2. Base 10 of x plus 2. What do you think that's going to do to my log graph? It's going to just move it left 2. So now with this one, you're going to have an asymptote here at x equals 2. And instead of going through the point 1, 0, it's going to go through the point negative 1, 0, right? Because if I shift it left, it's going to go through here, and it's going to go through negative 1, 0. You get that? Okay. What do you think would happen if I took a negative 2 and put it over here? What's that going to do to it? It's going to shift it down 2 units, right? So it's still going to have the same vertical asymptote. It's just going to go through lower like that, right? And so this point would get shifted down to, what would that point be now? If I pulled it down, right, would it be negative 1? Yeah, so this would be, so now you'd have a point on here, negative 1 comma 2, right? Negative 2. And then to find the intercept would be a little more complicated, which you'd have to use logarithm. All right? We're good? What about log? What about negative log of x? What would that do to it? That would make it go, like this, but it's not an exponential function. It's kind of going like, still going downhill forever, right? You ready to learn about natural logs? What's wrong?
I'm just confused on how you got those intercepts.
How did I get negative 1, 2? Because if I, or negative 1, 0, that one?
Well, are those both graphs of the log base 10?
No, this is this one, okay? The whole thing. This, if I take away the negative 2, okay, then it looks like this one, okay? Right? Because if it normally goes through 1, 0 and I shift it left 2, right, that point 1, 0 is going to be shifted left to negative 1, 0. And the asymptote is going to be shifted back 2, right? I should probably erase this one because it's confusing too. So then, yes?
Still how do you get negative 1, 0?
How do I get negative 1, 0? Because normal log base 10 of x goes through 1, 0, right? So if I move that back 2 points, it's going to go through negative 1. Yeah? Okay. Going back to, if I go back a page, right? Normally it goes through 1, 0. So I move that graph back, it's going to that. Okay. All right. Ready to learn about natural logs? Y, natural log of x. Y equals natural log of x. I like natural logs because I'm a pretty healthy person and I like to keep my logs all natural. So I only shop for my logs at Whole Foods. No, I can't afford Whole Foods. All right. So y equals natural log of x is the same as, it's the same as log base e of x. In other words, it's the inverse of y equals e to the x. So y equals e to the x and x equals e to the y are inverses of each other, and this is equivalent to y equals the natural log of x. It's base e, okay? It's base e, base, okay? So, and it exhibits some of the same properties as, all of the same properties as regular logs, okay? If I were to graph it, it looks like this. It also goes through 1, 0, okay? This is y equals e to the x. It has a point on here, 1 comma what? 1 comma e. Unlike the other, it also has the same horizontal asymptote, x equals 0. And, yes, sir?
I was just wondering how it goes through 1, 0, and 1 y.
Because, how could it do that? It, oh, I'm sorry, sorry. Sorry, because I'm confused, okay? It goes through the point E comma 1. Thanks, Tyler. Okay. I'm just getting warmed up this morning. E1, right? E comma 1, because it's the reciprocal, okay? And x equals it. Okay? So, using some of the same properties, what would be, so y equals natural log of e to the x is equivalent to saying that's equal to x. Okay? So a natural log undoes e. Okay? Conversely, e to the natural log of x is equal to what? X. Okay? So the natural log undoes the e to the power, and the e undoes the natural log. So what if I ask you what's a natural log of e to the 5th power? What's that? 5. Okay? What if I asked you what's a natural log? So these are kind of without your calculator. What would the natural log of 1 over e squared be? That'd be, see where Christian got -2? You can say, all right, so when I do natural log problems, I say e to what power equals 1 over e squared. That's the way I rewrite it in exponential form. E to the what power equals 1 over e squared. E to the -2 power equals 1 over e squared. Okay? I think you could sketch the graphs of some of those. Okay? And then I'm just going to look at an application problem, and then we'll be done. Okay? So let's pause. How long have I been talking? 23 minutes. So there are quite a few applications of logarithms in science and in math and in business. Okay? This is one application. Okay? So this is kind of interesting. Right? So this is just a formula that I guess the business guys figured out. But this model, t equals 12.542, natural log of x over x minus 1,000 if x is greater than 1,000, approximates the length of a mortgage of $150,000 at 8%. Well, right now, I doubt there's many mortgages that are $150,000 because most houses here cost way more than that. And 8% interest is kind of high, right? Now it's like 5% or 4% or something. But anyway, this is the formula you would use to tell how long it would take you to pay off your loan. So T is the amount of time it would take to pay off a loan of $150,000 at 8%. That, I believe, is where this $150,000 must be incorporated into this coefficient. And the 8%, I'm not sure exactly where that's incorporated into the formula, but the formula would change if those two things change, okay? So find the length of time if the monthly payment is $1,300. So what goes in here is 1,300. Okay, 1,300, and you just get T equals 12.542. Am I recording now? I'm recording, right? Am I recording? I'm recording. Okay. So 1,300 times the natural log. You don't need parentheses there, but I must. 1,300 over what? 300. Okay. And I plug that in, and I get T equals 12.542 times the natural log of that. Can anyone do that on their cut? Oh, why did I just rewrite it again? Okay. Do you get like 18 or something like that? 18. So this comes out to be about 18.4. Is that years or months? Years, right? How much would you pay? How much would you pay over that time? This is important if you're buying a car. A lot of you guys want to buy a car, right? So they use this exact same formula, just the numbers are a little bit different. Here's amortization formula. So how many months in 18.4 years? Well, it's 18 times 12 plus 0.4, so that's 4/12, right? 0.4 times 12 is what? Wait. It's about 5 months, right? So that's plus 5. How much is that? 221?
Well, okay, so when I multiplied it, 18.4 times 12, I got 220.8.
220.8. So about 221 months you're going to be paying mortgage payments. How much are you paying each mortgage payment? Times 1,300. 1,300. So I'm going to take that number. I'm going to take 221 times 1,300. Okay. I get 287,300. So how much are you paying for a house if you paid off in 18 years? You're paying, how much have you paid in interest? Shush. How much are you paying in interest?
A lot.
Well, 287 minus 150, right? Yep. Equals $137,300. So you're paying almost as much in interest as you are for that. But that's okay, because I have a 30-year loan that's bigger than that. My house, I'm going to pay off, like, it's going to be over $1 million. But hopefully I'll die before then, so I won't have to pay the whole thing off, so it'll be good. And leave my kids with all my debt. So, in any case, you can see that it takes a long